Okay, so we want to prove these statements about the symmetric difference, and the symmetric difference is defined this way, that it's the union of A minus B with B minus A. So for item A, we want to show that the symmetric difference of A and B is equal to the symmetric difference of B and A. So we're going to use an if and only if chain of reasoning. So we're going to say we have that X belongs to the symmetric difference of A and B, so A, B, and now we're going to apply the definition. If and only if X belongs to A minus B union B minus A, and now what we're going to do is we're just going to switch these around, because if I have, say, C union D, this is the same thing as saying D union C, right? So all we're going to do is switch around the order. If and only if X belongs to, that's going to be B minus A union A minus B. And now if you look at this, it's going to satisfy the definition of the symmetric difference of B and A, because you can see here that basically B and A have been switched, right? So wherever you have A, you can see that you have B exactly in the same placeholder, and vice versa. Wherever you have B, you're going to have A. So basically, we've just switched B and A around, and so this precisely satisfies the definition of the symmetric difference of B and A. So if and only if X belongs to the symmetric difference of B and A, right? So we've shown a biconditional that you can begin here and then reason, and if X belongs to the symmetric difference of B and A, you can get to X belonging to the symmetric difference of A and B, and vice versa. So we have shown a double inclusion, and our conclusion is going to be, therefore, let me write this. Okay. So fairly straightforward, and now let's do item B. So for item B, I'm just going to leave this line here because we're going to reuse it, and we want to show that these are the same. So similarly, we're going to use an if and only if chain of reasoning. So first we're going to let X belonging to the symmetric difference of A and B, and now we're just going to apply the definition. So if and only if X belongs to A minus B union B minus A. So now what we're going to do is we're going to unwrap this A minus B union B minus A. So if and only if X belongs to A minus B, or X belongs to B minus A. So we've unwrapped the union, and now we're going to unwrap the difference. If and only if, for the first one is X belongs to A, and if X belongs to A minus B, it means that X belongs to A and X does not belong to B, right? Or for the second one, it means that X belongs to B and X does not belong to A. So now what we're going to do is we are going to just rearrange this a little bit, because for this statement to be true, it means that one of them have to be true, right? It doesn't have to be both. So either X belongs to A and X does not belong to B, or X belongs to B and X does not belong to A. So one of these have to be true. Now, we're going to rearrange this and just say if and only if, and I'll explain it after I've rearranged it. We're going to say if and only if X belongs to A or X belongs to B. So we're going to say if and only if X belongs to A or X belongs to B, and we're going to say and X does not belong to A or X does not belong to B. So let's take a moment to think about what this means. So previously we were saying, hey, either X belongs to A and does not belong to B, or X belongs to B and X does not belong to A. So similarly, for this statement here to be true, now we have an and statement. It means that both of them have to be true, right? But we know that either x belongs to A or x belongs to B, and x does not belong to A or x does not belong to B, because the whole thing about the symmetric difference is that it cannot belong to both. So it's either in A or in B, and it's either not in A or not in B, depending, right? So if it's in A, it's going to not be in B, and if it's in B, it's going to not be in A, and vice versa. So all we've done here is we've rearranged it, but this is still true because of the definition of the symmetric difference. So once we're here, we're just going to say if and only if x belongs to A or B, it means that x belongs to A union B, right? And if x does not belong to A or x does not belong to B, it means that x does not belong to A intersection B, because remember, for it to belong to A intersection B, it has to belong to both of them. So if it doesn't belong to A or doesn't belong to B, it can't be in the intersection. And now, if it belongs to A union B and does not belong to A intersection B, this satisfies the definition for if and only if x belongs to A union B minus A intersection B. This is the definition, right? That belongs to the first one but does not belong to the second one. So from here, we have shown that if x belongs to a symmetric difference of A and B, it belongs to here. And also, we could have began the other way. We could have began here, and we would have shown that x is in there because we used if and only if statements. And so we have shown a double inclusion, and our conclusion is going to be, therefore, our conclusion is going to be A symmetric difference of A and B is equal to A union B minus A intersection B. So that's it for item B. Now we want to do item C, which is that the symmetric difference of A and A is the empty set. And the way that we're going to do this is by contradiction. So we're going to say suppose that, we're going to say for C, suppose that x belongs to the symmetric difference of A and A, right? Then let's apply the definition here. Then x belongs to, so now because this is A and A, we're just going to compare it with A and B. So basically wherever we have B, we're just going to plug in A. So it means that because this is A over here, we're going to plug in A wherever we see B, right? So x belongs to, let's see, that's going to be A minus A union, that's going to be A minus A, right? So this means, so x belongs to A minus A is just the empty set union the empty set, which means that thus x belongs to the empty set, which is a contradiction, right? Because the empty set has no elements. So the conclusion is, so x does not belong to A, the symmetric difference of A and A, which means A, the symmetric difference has no elements, because we just chose a generic x, right? We just chose any element in it. Has no elements, so it must be the empty set. It must be the empty set. So our conclusion is going to be, therefore, the symmetric difference is the empty set. So like I've said in a previous exercise, whenever we're dealing with the empty set, it's a great idea to use contradiction. So that's it for item C. And lastly, we're going to do item D. So let me erase this. Okay, so for item D, we want to show that the symmetric difference of A and the empty set is just A. So similarly, we're going to use a if and only if chain of reasoning. So for item D, we're going to say that we have that X belongs to A, symmetric difference of A and the empty set. And now we're just going to apply the definition, right? If and only if. So we're going to apply this definition, but instead of B, we're going to put the empty set wherever we find B. If and only if X belongs to, the first one's going to be A minus the empty set union, union the empty set minus A, right? And so if and only if X belongs to, well, A minus the empty set, that's just A, right? Because we're not removing, actually, wait, let me first remove the union. Let me unwrap the union first. So X belongs to A minus the empty set, or X belongs to the empty set minus A. So I unwrapped first the union, right? Now I'm going to unwrap this difference. So if and only if X belongs to A minus the empty set, well, A minus the empty set is just A, because the empty set has nothing, so nothing was removed from A, right? X belongs to A, or the empty set minus A is just the empty set, because the empty set has no elements to begin with, right? So, or X belongs to the empty set. And since the statement here has to be true, right, if and only if X belongs to A or X belongs to the empty set, since X does not belong to the empty set, it must mean then if and only if X belongs to A, right? It's the only way for this thing here to be true, because we definitely know that the X does not belong to the empty set. So we've shown by a double inclusion that if X belongs to A, then X belongs to the symmetric difference of A and the empty set, and vice versa. If X belongs to the symmetric difference of A and the empty set, then X belongs to A. So our conclusion is going to be, therefore, A symmetric difference with the empty set, that is just A. And that is it for problem 18.